Okay, we're back again on AtCoder. This is a very special contest right now, 299th contest. The next is 300th, so this is very special. It's AtCoder beginner contest, starts in 25 seconds. Thank you guys so much for tuning in, watching my videos. There will be more and more videos, so click that subscribe button down below. And yeah, yesterday we had the ACM contest in Slovenia, and I may do a recap on that as well. So let's go. Okay, given a string consisting of determine whether it's between the two, if so in okay, this is just like a string balancing problem. I will zoom in a little bit, maybe if s at I is this, then I will flip the current. If s I is this, if current is like 1, we'll see out in, else we see out, and we'll just return 0. Oh, there is integer here. Yeah, this should. Okay, let's get this. Good, and players playing a video. Wait, what? Bad gateway. Okay, something happened. Each player plays one card. Each card has two parameters, color and rank, both of which are represented by positive integer. Has color C and rank Ri. The ranks are different among the players. One winner says false if one or more cards with color T are played. The player who has played the card with the greatest rank among these cards, if no card with the color T is played, the player who has played the card with the greatest rank among the cards with the color of the see what happened here. If one or more card with color T, so T is given here, play the player the greatest rank. If no card with color T, then the player who has played the card with the greatest rank among the cards with the color played by the first player. Okay, just implementational task. Just what did it say? We're currently in contest mode and cannot access the list of submissions. I don't quite get it. Is my submission processed here? No. Okay. All right. Okay, so we just go, oops. T. This is C and R. So first there's C in the rank, then we go through each of these and we say if the color of I matches T, then we're okay. If it's not okay, then T is the color of the first player. Then we go through all of these and we say if T is, if color of I is equal to T, if R of I is bigger than R of R is R of I, the winner is I. Just see out the winner. Also. Okay, A we got accepted. Okay, for just auto refresh this. Nice. For a positive integer L, level L dangle string is a string that satisfies the following conditions. It's a string with length L plus 1 consisting of this, exactly one of the first characters and the last character. Okay, and the other characters are these. Okay, we're given a string S consists of n consecutive. Find the greatest positive integer x continuous is a level x. So I want to find what substring is like. This is easy. We just then we just go from left to right and we count like we have like out, so like some function will get the string S. This is current count of like this. We're gonna go and we are going to go through S and we're going to say if S of I is this whole thingy, then current plus plus, else, so we have like this current thingy, and we say that like answer is -1, answer is max, answer current 0, right? And then what we do is answer is max, answer, and solve from S, reverse S, and do the same thing here. Of course, just return answer. yeah, if current is 0, I want to continue. Okay, let's see. This is an interactive task your program has to judge. Okay. So if it's interactive task, I don't have this. Okay, the judge has a string. Let me see, submission gets accepted. Let's see, just standings. It has a string of length s of 0 and 1. Alright, you're given you're given the length n of the string, but not the contents. Instead, you can ask the judge the most running queries as follows. Choose an integer and ask the value of si. Print an integer p. So we choose some index and ask the value of si. Print an integer p such that p is not I see, yeah. So it's like this the middle thing here. This problem is like very well known. So if something starts at 0 and it ends in 1, we want to find where does it, like where from 0 it goes to 1. And how you do this is it's like with binary search. You ask, like if I ask for the middle element and it's like 0, then I suppose there is 1 on the right side, right? Yeah, just see the standings. Okay, cool. So there is n. This log 2 of 2 times 10 to the 5, 17, which means it's like we have like two more questions to spare. So you print out so if n is 2, we already know that this is 1. If it's not, let me see if I binary search this, is it correct? So if I detect 0 here, yeah, so it's like int l is 1, r is n plus 1, then r minus l is bigger, then mid is r plus l divided by 2. So ask about the mid question, if answer is 0, then L is mid, else R is mid or mid plus 1? Mid. And then I'm pretty sure, like, I could ask like one more question if like but I'm pretty sure it should be L here. Okay, let's start with this string here. Let me just confirm this. We have like 5 minutes to confirm this. Find by query. So if I say okay 7, then about 4. This is 0. 6. This is 1. 5 is 0. And it's 5. Yeah, this should, I think this should work. Let's just take some other random string which has like like this, which is 7, 4 is 1, 2 is 0, 3 is 0, 10 is 3. Okay, I think that should work. Nearest black vertex. Simple undirected graph. Okay, gets accepted. What place are we in? Oh, that's weak. You are given a simple undirected graph. Bidirectionally determine whether there is a way to paint each vertex black or white to satisfy both, and show such a way if it exists. At least one vertex is painted black. For every from 1 to k, the following holds. The minimum distance between vertex pi and a vertex painted black is exactly di. For each integer from 1 to k, the minimum distance between vertex pi and a black vertex is exactly di. Okay, so what if we start like a BFS from each vertex? So from each vertex that we have, so from each vertex that we need to do this, k, we start at DFS with like about D things, and then we mark these vertices in that region as having one of these black vertices, right? So it's being one of these here. So one of these vertices has to be black, right? Just add a page here. So technically from this vertex onto the distant, we're gonna push BFS and we're gonna say, okay, these vertices have one of them have to be black. And then from this vertex we're gonna push, and one of them have to be black. And then so we have some sets, some kind of sets. And essentially from this, but now these vertices, if I visit these vertices which are like smaller, if I visit these vertices and they have to be painted black, but they're in a smaller distance, then I have to just knock them out. Yeah. All right. I mean, yeah, sure. Let's call this. It's not simple problem to code, but shouldn't be that difficult either. So we read the graph as usual. We are just going to say that we have some bidirectional graph. Okay. And then for k of these, vertex, I will say vertex S, starting vertex and distance. And now I need the BFS here. I'm starting at that vertex. With my, so here is like paint, and now we're all going to say that they're all of the vertices are black, right? Okay, I'm going to say all the vertices are black. Also have like a distance here. Int maximum, like, and then I will have, okay, distance at S is 0. Can the distance be 0? Yes, it can be 0. Which means do I need to sort them by some like distance? No, probably not. So it says like if d is not 0, we're gonna push to the q s, right? And then top is q.front, q.pop for adjacency top a distance to v is bigger than the distance to the top element plus 1, distance to the distance top plus 1 q dot push v if distance of v is smaller than d, then call paint of v small. These are made like white, right? And then I mean here, if distance top smaller than the distance top is 1. Okay, this should paint the graph. Now we have some notes, and now we need to check if that's okay. So queries k, and queries at I, S, and D. Okay, we have to check if everything fits the, okay, and we need to print, despite both conditions, we need to print wait, for what? For every I, the following holds. There's no way to paint each vertex black or white to satisfy the condition, otherwise CS and print string representing coloring of the vertex in the second line and show S is a string for each I, 0 I is painted black and 0 if painted white. So it's actually our paint array but reversed. But we have to somehow check this, right? Also, we need to fill the dist here. Okay, so we have to check if SD is queries at I. So we fill the distances, say that this is 0, and then we say that if paint at if D is equal 0 and paint at S is 1. Okay, it's false. Also, we will push everything, but when we find if paint at top is equal to okay, if answer is not equal to the D, then okay, it's false. If it's not okay, see out. No. See out this. So answer is here. Answer is here. If paint of top 0, answer is the minimum distance top. This should kind of work. Okay, it crashes somehow. Do I? Oh, okay. Here is minus minus. No. Okay, let's see the paint array. Distance minus, or like even equal to the distance, maybe, I don't know. Right, if it's 0, 1, if distance is 1, then we need this is fine. If answer is bigger or wait, what does it say? Is the minimum distance between is exactly D. So it has to be exactly D. Distance, if it's painted, is 0. Oh, q dot push s. Okay, this should work. I mean, it's fine. Looks fine. Looks fine to me. Square subsequence. Gets accepted. Okay, you're given a string S consisting of lowercase English number of non-empty strings D that satisfy the following condition. The concatenation of DT is a subsequence of S, not necessarily S whose length is from 1 to 100. So you are given some string S, print the number of non-empty strings D, such that the concatenation of D is a subsequence of S. So I want for each of these subsequences of S, oh, not for subsequence, not necessarily continuous, okay, so not substring. Subsequence, okay, interesting problem. You can imagine like S are being like numbers from 1 to 26. And I want to find a subsequence such that it like repeats itself. That's another way of looking into the problem. So let's see G. We have sequence A of length n and integers between 1 and m. Okay. Every integer from 1 to m, it appears at least once in A. Among the length m subsequences of A, where each of 1 to m appears once. Okay, find the lexicographically smallest one. Okay, this shouldn't be that hard. I mean, it could repeat a lot of times. Interesting. Okay. In EX die some infinity. His unbiased 6-sided die and a positive integer r less than 10 to the 9. Each time the die is cast, it shows one of the 1 to the 6 with equal probability. Takahashi will perform the following procedure. Initially C is 0, cast the die increment C by 1. Let x be the sum of the numbers shown so far. If x minus r is a multiple of 10 to the 9, quit the procedure. Is multiple of 10 to the 9. Go back to step 1. Find the expected value of C. Multiple to 10 to the 9. Sound like when is the sum multiple of 10? This is some kind of mathematics. I think with mathematics or with like either with mathematics or matrix exponentiation. The expected value of C at the end of the procedure is approximately. If they calculate this value, it means like probably with mathematics, with like combinatorics, you can calculate it. But I'm not going to try. Okay, I will end it right here since it's still not finished. It's still, we have like 16 minutes, but I couldn't come up with anything on F and G. So I will just cut it out from the video, my thinking, because nobody probably will ever watch that. So the thing is that, okay, so let's go through the problems and explain them really quickly before I share my thoughts on F and G. And the contest hasn't ended, so I cannot show the tutorial, but maybe for better, so if you want to solve them on your own. Okay, so the first problem is like this: A, treasure chest. This is pretty not like known thing to do. You have like, this is kind of balancing bracket thing here, but you're given some sequence and you need to check if that star here is inside of two brackets. So when you open up a bracket, you just invert that balance here. I solved it that way. B, really straightforward implementational problem. I won't just take a lot of time here. It's, you just have to see if first there is a color with T. If there is no color T on any of the cards, then you set T to C0, and then you find the winner of these cards, and this is off and everything. So here that's pretty straightforward. This C problem, yes, pretty straightforward as well. You just count these zeros, and when you reach to a dash, you kind of maximize the answer, but you have to do it both ways, so from one side and from the other. Pretty straightforward. That's why I wrote this solve function. This is a lambda function. D, also kind of straightforward, right? Just so D is like very well known, because if you have some function which starts from some point and ends in some point, that. And they say that like it's a continuous, even though we have like discrete function here, but it's like not it's like continuous. So this function doesn't really have like jumps here like this. And if some function is like that, then it means that there will be some point where it goes, where if you have like two values here, like for our case it's just like this. It's just like if 1 and 0 for our case is just like this function. And you could jump more, but let's imagine this is 100. Then like you could have something like this. And then if you say, okay, does it go through 50 or through any number from 0 to 100? If it's continuous, it must go. And there is a point in which this happens. But this is easier problem because it's like here 1 and 0, and you just have like this maybe. And then you want to binary search where this point occurs. And I just say it like this, first at the middle, and if it's 0, I know that I can move this 0 over here, and I can just say that this is like, I don't care about this, because this is the same idea. And then I move this 0 here, and then I look at this range, and now here, let's say 1, here it's like, let's say 1. And then I know that I can move this one here without taking care of this range. And then you see here there is still like this how do you say, like a switch from 0 to 1, this up edge. And then you find this up edge just by binary searching, and that's it. And you can prove that binary search logarithm of 2 from this number is like 18, 17 point something, like 18, and then you have like 2 more questions just to be sure if you want. But with this binary search, you don't need to answer any additional questions after you find this, after you find the point. of switch. Okay, so this has been D. E is also a straightforward problem. So if you're given this graph, you want to know this black. So for every like SI, the minimum distance after some distance DI, you want to have a black node here, and this to be the minimum that you that distance to a black node. Exactly. So if you just search, if you like have like graph like this, you can clearly see that all of these nodes cannot be black, because if any nodes with the smaller distance are black, then the smallest distance is this instead of this. And then what you do is you color them all white here. So you color everything white, but first initially all nodes are black, and then you color everything white, which are like smaller than the distance, and you do this from all SIs, so from all terminal nodes. Let's say these are like terminal nodes here. And then when you do this, you have to at the end check if these conditions are satisfied. And I just run one more time from each SI, one more time BFS, and check if the minimum distance to a black node is the same here as the distance that I want to be, right? It's just twice DFS running from each node doesn't really make a difference. Okay, so my thing on F and G, my considerations for F and G is like F is like some kind of dynamic programming problem, but I have no clue how to solve it. I don't know. G is kind of good problem. I would say I want to know the solution of G. And what I did is like tried some greedy solution, but of course it failed. So the greedy solution is just like taking all of these numbers from back and just saying if this number that I'm considering is smaller than what I have as the first number in the permutation, then I take it. But there exist cases such like these, which I drew here somewhere. Yeah, here. So if I have some numbers, so I always show the numbers as like points. So these are indices here on this axis, and these are the values of the numbers. And I have already some permutation like this. And now this is my first number in the permutation. Okay, this is some permutation. Here are some not taken numbers. Let's say here like some not taken number, here some not taken number. Let's say here is some other not taken number, right? But there could exist this number and the same number as it. But there could exist a couple of better numbers and maybe a couple of worse. Like all of the numbers are worse numbers. So no number is like better than both of these. So better number means lower. Okay, so all of these numbers are kind of worse. But in a sensible way, if I take this number, then it's much better to take these as well, let's say. Like, now in this case, like this would be still maybe better, but let's say this kind didn't exist. Yeah. Maybe you want to take some of these numbers and then do some of like these numbers here, which I haven't taken, right? And in the sense of way, I could probably overwrite like this number. If we take this number, I could probably overwrite many of some other numbers here. And what I was thinking is like, I don't know. I don't know. I may like try it, but I want to first see like the tutorial at least if I'm on the right path. But it could be some data structure, some kind of data structure that does this pretty fast, or you could like keep like kind of continuous functions, maybe like set like decreasing things here like, and then you could probably maybe somehow like over rule previous such things with new. But I'm not sure. I'm really not sure. And yeah, I would cut this out from video. My thinking of this, because I have solved all of the problems in. I mean, through F in like 34 minutes. So I don't consider anyone watching 40 minutes of thinking for like F and G. Yeah, thank you guys so much for watching, and I see you in the next one.